Good morning, students. Today we'll start section 3. In this section, we will discuss about modules. Module is a generalized concept of a vector space. In a vector space, we restrict the scalars to lie in a field. But here, in case of modules, they are allowed to be the elements of a ring. So first of all, let us define module. To define a module, let us take R be a ring and M is abelian group under addition, together with a mapping from R cross M into M called left scalar multiplication. Means for each R belonging to R and M belonging to M, there exists a unique element Rm which belongs to M. Then M is called left R module if the following conditions are satisfied. In the first condition, for the scalars R and S belonging to the ring R and M belonging to M, R plus S into M is equal to Rm plus Sm. The second condition is for the elements M and N belonging to M and R belonging to ring R, R into M plus N is equal to Rm plus Rn. In the third condition, for M belonging to M and Rs belonging to ring R, Rs into M is equal to R into Sm. And this condition is additional if the ring R has identity element as 1, then identity into M, that is M. So if the ring R has identity element, in that case this condition is also satisfied. Otherwise we have these three conditions. So we say that the abelian group M with the scalar multiplication defined in this way, which satisfies these conditions, that is called left R module. In the same way, we can define the right R module. In the right R module, that is also an abelian group under addition. Here the mapping we define from M cross R into M, which is called right scalar multiplication. Means for each R belonging to the ring R and M belonging to M, there exists a unique element Mr, which is an element of M, and the following conditions are satisfied. First condition, M into R plus S is equal to Mr plus Ms. Second condition, M plus N into R is equal to Mr plus Nr. Third condition, M into Rs is equal to Mr into S. And if the ring has identity element, then M into 1 is equal to 1. This 1 is the identity element of the ring R. Here Rs, these are the elements of the ring R, and M and N, these are the elements of M. If the ring R is a division ring, in that case, the left R module, that is called a left vector space over the ring R. And if we have right R module, that is called right vector space over the ring R. And if the ring is commutative ring, in that case, left R module and right R module both are same, because in that case we have Rm is same as Mr. So in this case, we simply call them R modules. Now let us see some examples of modules. Our first example is if A is additive abelian group, then A is left as well as right module over the ring of integers. let us denote this abelian group by M, and the ring of integers we have denoted by R, because we know that the group is abelian group under addition. And now we can define scalar multiplication by taking an element R from the ring R and an element M from M. We define the scalar multiplication Rm by M plus M plus M and so on R times if R is positive. If R is 0, then we have defined Rm to be 0, and if R is negative, we have defined Rm as minus M added R times. So we have defined the scalar multiplication in all the cases, and in each case this scalar multiplication Rm belongs to M. Now we are to verify the other 4 conditions. In the first condition, we take R and S, 2 elements from the ring R, and M from the additive abelian group M. Now let us find R plus S into M. Now by definition of scalar multiplication which we have defined, R plus S into M means M plus M plus M. This is R plus S times. So this can be written as M added up to R times and M added up to S times. M added R times, this is Rm, and this is Sm. So R plus S into M is equal to Rm plus Sm. Now in the second condition, we take M and N, 2 elements from M, and R from the ring R. Now R into M plus N means M plus N added up to R times. Then it can be written as M added up to R times plus N added up to R times. This is Rm and this is Rn. So we have proved the second condition, R into M plus N is equal to Rm plus Rn. Now in the third condition, we take 2 scalars R and S from the ring R and 1 element from M. Now let us find Rs into M. It means M added up to Rs times. Now this can be written as M added up to S times and so on, and this is R times. So we get this will become Sm, this is Sm, 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 R times. So we get R into Sm. Now because identity element belongs to the ring of integers and identity into M, that is M, for every M belonging to M, so all the conditions are satisfied. So we can say that M is a left module over the ring of integers. In the same way we can prove it right R module also. Now our next example is every ring is a module over itself. So let us consider a ring R, and we have denoted it by M here, and we are to prove that M is left R module. Now by definition of ring, a ring is abelian group under addition. So our first condition for being a module is satisfied. Now we define scalar multiplication by taking an element R from the ring R and an element M from M. Here M is also the same ring R, and we know that a ring is closed under multiplication. So because both elements are the elements of ring R, so Rm, that is also an element of M. M means the ring R. So we have defined the scalar multiplication also. Now let us verify the other 4 conditions. Let us take R and S, 2 elements belonging to the ring R, and 2 elements M and N belonging to M. M is actually the ring R, so M and N are also the elements of the ring R. Now let us verify the conditions. First condition, R plus S into M. Now, because in a ring, right distributive law holds. So by that law, this can be written as Rm plus Sm. Our condition is satisfied. In the second condition, we find R into M plus N. Now, in a ring, left distributive law also holds. So by that law, this can be written as Rm plus Rn. In the third condition, we have Rs into M. Now, because R, S and M all are the elements of ring R, and in a ring, associative property holds. So, by associative property, this can be written as R into Sm. And the last condition, if the ring will have identity element, in that case, identity into M, that is M. So, all the conditions for being a module are satisfied. So, we can say that every ring is a left module over itself. Similarly, we can prove it right module over itself. Now, our next example is M is a set of all M cross N order matrices over a ring R. Then we prove that M is a module over the ring R. Now, the set of all M cross N matrices, that is a abelian group under the addition, where the addition of matrices can be defined in the way, if we take two matrices A and B from the set M, A we have denoted the entries of matrix A, we have denoted by Aij, and entries of matrix B we have denoted by Bij. Now we can define A plus B because A and B both are matrices of M cross N order. So A plus B is also a matrix of order M cross N. Now let us define the scalar multiplication. To define the scalar multiplication, let us take R belonging to the ring R and a matrix of order M cross N belonging to M. The entries of matrix A we have denoted by Aij. Now let us define the scalar multiplication Ra by multiplying each element of the matrix by R, and this is again belonging to M because this is also a matrix of order M cross N. So we have defined scalar multiplication also. And we can easily verify the remaining four conditions, that if we take R and S belonging to ring R and two matrices A and B belonging to the set M, then the four conditions R plus S into A is equal to Ra plus Sa. Second condition, R into A plus B is equal to Ra plus Rb, and Rs into A is equal to R into Sa, and identity element into A is equal to A if identity element belongs to R. So these conditions can be easily verified, and so we can say that M is left R module, and in the same way we can prove it a right R module also. So we can say that M is a module over the ring R. Now our next example is every left ideal of a ring R is left R module. So let us take a ring R and I is left ideal of this ring. Let us denote it by M. Now by definition of ideal, ideal is abelian group under addition. So we can see that M is abelian group under addition. Now we define the scalar multiplication. So let us take an element R belonging to the ring R and M belonging to the ideal I. Now because I is an ideal of R, so by conditions of ideal, R into M belongs to the ideal. So we have defined the scalar multiplication also. Now the other four conditions. In the first condition, we have R and S belonging to the ring R and M belonging to the ideal I. Now R plus S into M. Because R and S are the elements of ring, M is element of ideal I and I is also contained in R. So we can use right distributive law in the ring R. So by that law, this can be written as Rm plus Sm. In the second condition, R into M plus N. R is the element of ring R. M and N are the elements of ideal I. And they are also belonging to the ring R because I is an ideal of ring R. So we can use left distributive law. So by that law, this can be written as Rm plus Rn. In the third condition, we are having R and S belonging to the ring R and M is element of ideal I. Again, M belongs to the ring R also. So we can use associative law. By associativity, this can be written as R into Sm. And the last condition, if the ring has identity element, in that case identity into M, that is M. So we have verified all the conditions for being a left R module. So we can say that every left ideal of ring R is left R module. Now let us see one more example in which we prove that direct product of two modules is again a module over a ring. So let us take M and N are two modules over the ring R and we define their Cartesian product M cross N. M cross N, in M cross N we define vector addition and scalar multiplication in order to prove it a module. So first of all, let us define vectors addition by taking two ordered pairs from this Cartesian product. One ordered pair we have denoted by x comma y and second pair x dash comma y dash. So by coordinate wise addition, we get x plus x dash, the first coordinate, and second coordinate y plus y dash. So we have defined this vectors addition in M cross N. And we define scalar multiplication by taking R belonging to the ring R and this ordered pair belonging to M cross N. We have defined the scalar multiplication by multiplying x and y by R. So we get the ordered pair Rx, Ry. Now M cross N is a module over the ring R which is called direct product of the modules M and N. Now to prove this, let us denote M cross N by M dash. Now first of all, let us verify that this direct product is abelian group under addition. Now because M and N are modules, so they are abelian groups under addition. So their direct product, that is also an abelian group under addition. Now for the scalar multiplication, let us take an element from the ring R and an ordered pair from M cross N. We define R into the ordered pair xy is equal to the ordered pair formed by Rx and Ry. Now because M is a module, so Rx, that is an element of M, Ry is an element of N. So this ordered pair, that is an element of M cross N. In this way, we have defined the scalar multiplication in M cross N. Now it remains to verify the remaining four conditions. In the first condition, we have taken two scalars R and S from the ring R, an ordered pair formed by the elements x and y belonging to M cross N. Now, by definition of our scalar multiplication from here, this can be written as the ordered pair formed by R plus S into x and r plus s into y. Now because m and n are modules, m is module, so this can be written as rx plus sx. N is module, so this can be written as ry plus sy. And by definition of addition, which we have defined, this can be written as the sum of the ordered pairs formed by rx and ry, sx and sy. And again, by definition of scalar multiplication, this can be written as r into the ordered pair xy plus s into the ordered pair xy. Our condition is satisfied. Now in the next condition, let us take two ordered pairs belonging to m cross n. One ordered pair we have denoted by the ordered pair x comma y, and second we have denoted by the ordered pair x dash comma y dash. Now let us find r into the ordered pair xy plus ordered pair x dash y dash. Now by definition of vectors addition, this addition can be written as the ordered pair x plus x dash comma y plus y dash. Now again, by definition of scalar multiplication, this can be written as r into x plus x dash comma r into y plus y dash. Now again, by using the properties, because m is a module and also n is a module, so by their properties, this can be written as the ordered pair rx plus rx dash comma ry plus ry dash. And again, this can be written as the sum of the ordered pairs formed by rx and ry, rx dash and ry dash. Again, by definition of scalar multiplication, this can be written as r into the ordered pair xy, and this can be written as r into the ordered pair x dash comma y dash. In the next condition, we are having r and s belonging to the ring R, and the ordered pair xy belongs to m cross n. Now, by definition of scalar multiplication, this can be written as the ordered pair formed by rsx and rsy. Again, by definition of scalar multiplication, we can take the scalar r outside. So this can be written as r into the ordered pair formed by sx and sy. Now this can further be written as r into s into the ordered pair formed by x and y. And if the ring R has identity element, in that case identity into the ordered pair xy. Again, by definition of scalar multiplication, this can be written as identity into x comma identity into y. So we get the ordered pair xy. So we have verified all the conditions for being a module. So we can say that direct product of modules is again a module. Here we have proved it left R module. In the same way, we can prove it a right R module. So these were some of the examples of modules.